Okay, so in this video, we're going to be talking about our first DC-DC converter, which is called a buck converter. So before we get into that, let's talk a little bit about why we would want to do one. Okay, so let's start by thinking about the ESP32 that we're using in the lab. We've just been using a 5-volt USB plug, but it can be powered up to 12 volts. So if it's powered by 12 volts, but the outputs only put out 5 volts, or 3.3 in the case of the ESP32, then where'd all that voltage drop? And so we need to be able to change voltages, DC voltages up and down to get it to work out. So in order to look at this in a little more detail, let's look at this just as the simplest case as like a heater. So let's say you're going camping and you want to bring a battery powered heater. So you're going to get 2 car batteries, tie them together and get 24 volts. And we're going to get a resistor across there to create 100 watts of heat. And then we want to take that 100 watts of heat and we want to control it and change it from 100 watts down to, sorry, from 1,000 watts down to 100 watts. Okay, so let's go and let's pull up and look at some numbers here. Okay, so what we had is we said that we wanted to do 2 batteries. So we have 24 volts, and we are going to create a resistor such that this is a 1,000-watt heater. So nice and warm. Okay, so with this 1,000-watt heater, we need to figure out what the battery needs to be. So our voltage is 24 volts, and our power is equal to V squared over R. So we have 1,000 equals 24 squared over R, which creates a resistance of 0.576 ohms. And then we get ourselves our 1,000-watt heater. So that's all great, but now it's a little bit too warm, but we still want it on. So we want to change this to be a power of 100 watts. So it still produces some heat, but it's not as much. So how do we do that? Well, we're going to have to do that by either changing the current or changing the voltage across our resistor. And we're going to have 2 ways to do this. The first way is, well, we love our old voltage divider. Okay, so now this is what we have. So we have our 24 volt supply. We're going to put a resistor here. We're going to put our 0.576 ohm resistor right there. And we want to change the voltage. Okay, so what voltage do we want? Well, now we want 100 watts, which is equal to V squared over 0.576. Now we're changing the voltage. We solve that, and so we're trying to get a voltage of 7.59 ohms. Okay, and we're just going to do that using a voltage divider. So now we have 0.576, which is our heating resistor, divided by 0.576 plus our new resistor times our 24 volt supply equals 7.59. Whoops, that is not ohms, that is volts. Volts. Okay, we don't have to put the units on. So we solve this and we see I'm just going to get a resistor of 1.245 ohms, and then this will work out. So in order to do this, it should work, but now we want to look at the efficiency. So our efficiency is defined as P out over P in. Okay, well, our P out is our 100 watts. Great. What is our P in? So our P in is going to be equal to V squared over R, which is going to be equal to my 24 volt squared divided by 0.576 plus 1.245. So my P in is equal to 316. So we divide this by 316 watts, and we get 31.7% efficiency. So really what are we doing is we are throwing away 216 watts. So we're basically saying I have 216 watts, I'm just going to throw that away. And so I'm really throwing it away in heat. Well, that's not very good because now our battery isn't going to last as long and it's generating lots of heat that we have to get rid of, and we only wanted 100 watts in heat. So we're smarter, we've come a long ways, and so we're going to come in here and we're going to use a MOSFET as a current source. Well, that sounds way better than just using voltage dividers. So let's look at what this model looks like now. So now we have our 24-volt power supply. We have our resistor, 0.576, and we are going to create ourselves, use a MOSFET, and we're going to give it some input voltage, right? So I can control this voltage. It's not putting out any significant current, it's just controlling. So this is some V in. Well, let's look at using the IRF 530. Okay, so it has a threshold voltage of 4 volts and it has a KP of 5. Okay, so we're just going to control the input voltage until this V in right here, until we get the current that we want. Well, how much current do I want? Well, let's go look at that. So we want power is equal to 100 watts, which is equal to I squared times 0.576. So I'm trying to get an I of 13.18 amps. Okay? So I just adjust my V in until I get the right current, and then everything works out great. Okay, so let's look at our efficiency. So my efficiency, again, is P out over P in, which was, well, this one was 100 watts like we had before. And now we got to figure out how much power is going in. Well, then we're just going to use VI, which is equal to 24 times 13.18, which is equal to 316 watts. Well, that was the same thing that I had here. So what we see here is that my input power is the same. And so the difference is rather than dropping my power across a resistor, I'm just dropping my power across my MOSFET. So I can use the MOSFET as a controllable resistor almost. And it's just as inefficient. I have the same efficiency that I had before, 31.7%, and I'm throwing away all of my power into my MOSFET. So this isn't exactly what I want, okay? So we need a better option to do this. And so what we're going to be able to do is we are going to basically turn a source on and off, okay? So let's look at my third approach, which is this is my 0.576 ohms, my 24 volts, and so I'm going to create a signal that looks like this. Roughly, right? You get the idea. So what's going to happen is we are going to produce 1,000 watts 10% of the time. Okay? So if I produce 1,000 watts 10%, then my average power is going to be 1,000 watts times 0.1 is equal to 100 watts. So that means that everything is going to work out just fine. So now what is my efficiency? Well, my efficiency is going to be P out over P in, which is going to be 100 over 100. So we get 100% efficiency on this because it's just turning on and off. Now as a heater, this would work just fine because my average is going to average out over time. It's going to get really hot. If this was on the order, if this time scale here was on the order of, an hour, that would be bad, right? Because that means it's just on for a couple minutes, super, super hot, and then it's off. If this is on the order of 1 second, then I'm not even going to notice the difference because it's going to be turning on and off and kind of average out. The problem is that there are some cases where we want a nice smooth voltage. If I'm applying this to my Arduino, that would be bad, right? Or my ESP32. I want a nice uniform. Don't plug your cell phone into something like this because it'll ruin your cell phone. So we want to get a better way to smooth it out. So in order to smooth it out, oh, well, I'm just going to throw a filter onto the end. So let's look at this. So here is my 24 volts. I have my switch. I'm going to use an inductive filter that looks like this, 0.5. We'll just call it R now. And I have an inductor there. Okay, so this is, and then I just have this switch that's opening and closing and filtering everything out. Okay, there's a big problem here. Okay, and the big problem here is that we remember from 240 that the voltage across an inductor is L di dt, which if when I open my switch, I'm going from flowing current to no current at all, and so that becomes infinite. Oh, infinite is bad, okay? So the infinite in reality wouldn't be infinite, but I would get a big voltage spike and I get this arc, and that arc can damage things. So what I need is I need a current path for the current in the inductor. Otherwise, we don't ever want to open the inductor up all the way. So what we're going to do is we're going to create something that looks like this. Okay, so my switch is either going to be in the up state, right, connected up to this part, or it's going to be down there. And so in that case, my voltage has current or no current, but I always have current going through my inductor. It's either being charged by the 24 volts or it's discharging. And so this won't create that arc, and then everything works. Now, I don't want to be sitting there when I'm camping and throwing the switch up and down and doing all of that. I want to do this electronic. So I need a way to make an electronic switch. Well, I'm going to use the MOSFET as my electronic switch. Okay, so the problem is that the MOSFET, let's draw our little MOSFET. Okay, this is can be modeled as a switch that's controlled by my control voltage. The problem is this is called a single pole, single throw switch. It's either connected or it isn't. We need to be able to swap between the two. Up here, this is a single pole, double throw switch. So I need to configure my structure as a single pole, double throw switch, which I can do that with two switches. So what we're going to do, the first option, let's do option 1, is we're basically doing something that looks like this, that has two switches. And each switch is modeled with a MOSFET. Okay, so what does this look like? This is going to look like throw an inductor in there. Let's draw this the right way. And then I have those two control voltages that's going to throw my switch. Now, most of the time, this is actually drawn completely vertical, where my switches are vertical. So it's usually drawn like that, right? Okay, so this is option one. Option two, and then when I do this, I have two control voltages because I got to make sure that the switches aren't on at the same time and everything is working out. The second option is, well, I can use a diode as kind of a passive switch. So in that case, I take this one right, well, we'll take this one right here. And what you're going to do is you're going to take this switch right here and replace it with a diode that acts as a switch. Now it's going to naturally switch and you don't have to worry about getting the timing and having two control voltages. And so the diode, this diode right here, when this switch is connected, you see then the voltage at this point is going to be higher than the voltage at that point, and this diode is going to be open. Then when this switch goes open, the voltage right here, this inductor is going to cause the current to flow through here, and then the diode turns on. Okay, so this configuration right here is called a buck converter. Okay, and it's basically just a PWM, a pulse width modulated signal that has an inductor as a filter. And then if you want to get fancier, I can do another pole filter and I can come in here and you can even add on a capacitor there to smooth it even more. So then I get a two-pole filter. So this is the basic buck converter that we're going to be analyzing.